Hi all, in this video we'll talk about topological sorting. First we'll see the definition of topological sorting and then we'll see the different ways of achieving it. So the textbook definition of topological sorting is it is a linear ordering of vertices, okay, such that for every directed edge u comma v, vertex u comes before v in the ordering. So what does that mean? Now let us consider a graph and your graph contains vertices starting from A to E. Now I have arranged these vertices in some order. Okay, now I have taken, this could be one order E, D, B, C, A, and other order could be A, B, C, E, D, and other order could be D, A, D, A, E, and then C, B. So these are all the different ways of arranging these five vertices, right? So if you take any order, like let's say this order will become topological order if, let us consider that this is a topological order, and this order can be set as a topological order only if it satisfies the below conditions. So now this is the EDBCA, right? Now let us assume there is an edge from E to D, okay, E to D. Let us assume that there is an edge from E to D in the graph, okay. Then according to this definition, for every directed edge UV, U comes before V. Yeah, there is an edge from E to D in a graph. Now I have arranged in my topological order, E came before D. So that is fine. Now there would have been edge from V to A all as well. Okay. Now let us consider my graph is this way. Then so let us consider this is my graph, a directed graph. Now if you see E, there is an edge ED. So in my topological order, this is a directed edge U and this is a V, okay. Now in my topological order, E came before D, okay. Now this is fine. And let's check for the second edge. D should come before B because there is an edge from D to B and D should come before B. Yeah, D came before B in my order, okay. Done. And here D, like A comes after D, like D should come first and A should come after that. So if you see, these need not be adjacent, okay. Now here D is at second place and A is at the last place. This is also fine. It need not be adjacent, but it should come before, okay. Yeah, it is the same. And even if you see this edge EC, then E should come before C. Here if you see E is here and C is here. So if you take in this particular order, if you take any edge and if this satisfies the this condition, like if you take any edge and if you see in the topological order and according to the edges, if U comes before V in the topological order like we saw now, then we can consider that as a topological order. Now let us see the second order. Like during some traversal I have obtained this order. Now let us see this will become topological or not. Here if you see, D should come before A. D should come before A. But if you see here, D is at the last. A came before. So this is not a topological order. So the topological sorting is nothing but if you have a graph and if you arrange the vertices, or if you arrange the vertices in such a way that all the vertices should follow this rule, like U comes before V, like whatever whatever order I take, if you compare with the edges, then these should follow the order like how we discussed now. Now why is it actually required? Why is the topological sorting required? Topological sorting is basically like a dependency. Now according to the topological sorting, if you see here, E should come if you take this, E should come first, right? So what I'll do, I'll write E first and then I'll write D second. Even here B should come after D. I'll do this way. and C should come after E. I can put C should come after E. It can be here, it can be here, or it can be here. It can be anywhere. Okay. And A should come after D, right? After D, it can be here, it can be here, it can be here. So you can, like when you are fetching a topological ordering, you cannot get a unique topological order. It might be possible that you might have multiple topological orders. Okay, but it's just that it should follow the order, like it should follow, like who should come first and who should come next, that order should be followed. And why is it actually required? Topological sorting is actually required in so many real world applications. Now let us say a person is doing some PhD. So there should be a criteria, like even if you see in the applications you will have criteria, right? Like the person would have had degree with so and so percentages, then only he is allowed to do the PhD. Or let us say a person is studying 10th class. First he has to complete 5th class, then he has to complete 6th class, then he has to complete 7th class, like 5th, 6th, 7, 8, 9, 10. So like without if you want to write a board exam of 10th standard, then you have to complete 5, 6, 7, 8, 9 classes directly. You can't go from 5th to 10th. There is a certain kind of ordering or dependencies, right? So if you take the courses also, let us say I want to take some 5 courses, and among the 5 courses, let's say now the 5th course, if I want to take the 5th course, 4th course has to be, my prerequisite is 4th course, and for taking the 4th course my prerequisite is 3rd course. So you will encounter a lots of scenarios like this in real world, right? Where to achieve something or to work on something, you have to complete few other things. So you can represent that in terms of graph. Let us say there are 5 courses, and if you see here, 5th course would be taken only if 4th course is completed. And there can be a chance also, like if I'm taking 4th course, the criteria is I have to complete 3rd course, and some other, like another condition can also be either I would have completed 1st or 3rd. Okay, this could be also a condition, right? Like usually in a B, like if a person is doing a BTech, one criteria is they have to come via MSET exam, and the other criteria is they would have had this like after inter, they would have had some internship kind of thing. Okay, so there could be multiple criterias for a job. Okay, so that's why, like for 4, like to take the 4th course, either you would have had this first course, or you would have had 3rd course. Either one of these should be fine. Okay, so many real world applications can be represented in terms of topological sorting. Okay, basically this is like dependencies. Like if you want to execute a first one task, before that some other tasks has to be completed. Okay, and if you see the topological sorting, it can be possible only if the graph is directed acyclic graph. Why I'm saying directed acyclic graph? Because let us say I take some directed cyclic graph. Okay, if I take a directed cyclic graph, I'll show it in the slide. Now I'll take a directed graph, and which is a cycle. Okay, now these are the 3 vertices. Okay, these are the 3 vertices, and here there is exists a cycle. Now this is A, and this is B, and this is C. For B, to take B course or to work on B, first I have to complete A. Okay, and to work on C vertex, I have to complete B. Okay, then this is fine. Like AB is one ordering and ABC is one ordering. Okay, but here can I what is the prerequisite of A here? You have to complete C. Okay, to complete C, so to take course A or to work on some job A, then you have to complete C. But C will be completed only if B is done. C will be started only if B is done, and B will be started only if A is done. So it's like there is a cycle. So we cannot predict which one has to be taken first. Like if there are three courses like this, where you for to take C to take course C, you have to complete course B. Okay, and to complete course B, you would have taken course A. Okay, then if there is no cycle, then what a person will do, first he'll join for course A, and then he will take course B, and then he will take course C. But if there is no cycle, this is the way. But if there exists a cycle, then what he will do, there will be one more edge like this. So to start A, you would have completed C, and then for C there is a dependency, so you will not get a definitive order in which you should take the courses. That's why this topological sorting you cannot do in a directed, if there exists a cycle, you cannot determine a topological sorting, right? That's why if a directed graph has cycles, then you cannot determine topological sorting. Then if you come to undirected graphs also, and you know, right, graph is a bidirectional. Now this if you have two two vertices, you will have directions like this. So which one comes first and which one comes next, you cannot determine that. So that's why topological sorting is possible only in the directed acyclic graphs. Okay, now how to determine a topological sorting? Now you have a graph and how you want a topological order. Now let us say I have this graph. You can consider these courses also. I have three courses, like five courses, and there is some order in which I should take the courses, and what is the order. So to determine that order, there are two ways actually. One is using DFS and the other one is using BFS. So BFS method is also called a Kahn's algorithm. In this video, we'll determine topological order using DFS. In the coming video, we'll discuss about the BFS method. Okay. Now, if you remember the DFS, yeah, this is a sample graph on which we will determine the topological order. If you determine DFS, how to do? Let me write the DFS order here. Okay. So let us assume, by looking at that, we can write a DFS, right? One is 0. Like let's say I'll start from 0. Okay. Yeah. So first I'll start from 0. Then I'll go to 1. From 1, from when I start from 0, I can either go to 1 or 4. Now, if I choose 1, I can go to 2. If then from 2 there is no option, then I'll trace back. Then I'll trace back. Then from 0, I'll go to 4. Okay. From 4, I can go to 1. But since it's already visited, I'll not visit it. And there is an edge from 3 to 2. This is also. So if you write a DFS order, what you will do, the DFS order will become 0, 1. Because in DFS, what you will do, whenever you visit a vertex, here first you visit 0. Then you will print it. As soon as you visit a vertex, you print it. So I visit 0, I print it. Then I go to 1 here like this. Then I print 1. Then I go to 2 here. Okay. I print 2. From 2, there are no ways. There is no edge, right? So I'll trace back. I'll trace back. From 0, I can go to 4. Okay. And then from 4, since 1 is already visited, I will not print 1. And then if you see, are there any vertices that are not visited? Yes, 3 is not visited. So this is the DFS order. Okay, so in DFS, what are we doing? We are printing the vertex as soon as you visit it. But, or you are pushing it to the stack. Let's say I have a stack, okay. So in DFS, we use the stack, right? So what you will do, you will push a vertex to the stack as soon as you visit it. Now I have what would be the stack in like if you do a not traditional DFS method, first 0 would be there. Next I'll go to 1. Next 2 would be there. Okay. Now 2 would be there. After that, what you will happen, you will pop out 2, you will pop out 1, and then you will put 4. Okay. Now after from 4 you have an edge, but this is already visited. Then there is no way from 4. You will pop out. Then you will put 3 here. Then after that you will pop out 0 as well, because there is nothing from 0. Then you will put 3 here and then you will pop out. So what are you doing? You are printing as soon as you visit a vertex. One thing you are doing is you are putting it to the stack and you are outputting it as well. In your output you are adding it. But the topological sorting is opposite to that. So what you have to do is, as soon as you visit a vertex, don't push it into the stack. Okay, you should not push into the stack as soon as you visit it. So here for the process in topological sorting is, when you come back, when you trace back the path, then you push to the stack. Okay, when you trace back the path, you push it. So it is quite opposite to the DFS. In DFS, when you trace back, you are popping out. Here, when you trace back, you push it to the stack. Okay, you should follow a traditional DFS method, but the point at which you push to the stack is different. Okay, so now I'll follow a regular traditional like a regular DFS. Okay, first I'll start from 0, then I'll go to 1, right? So from 1, uh, like I can choose either 4 or 1, but I'm choosing here 1, and from 1 I can go to 2. Okay, from 2 there is no path. So what I have to do, I'll trace back. And the condition in the topological sorting is, when you trace back, you push it to the stack. Okay, so when I trace back, I push it to the stack. Now from 1, is there any other way? No. Now you trace back. So when you are tracing back, you should push it to the stack. I did that. Now from 0, what happens? There is another way. You go to 4. Okay, from 4, what is there? There is another edge one, but that is already visited. So there is no other way from 4. Now I trace back. Now while trace backing, push it to the stack. Okay, now from 0, you don't have anything, like you don't have any other ways. So what you have to do, you will trace back from 0, right, basically. So then you put 0. Now there is another vertex 3, and from 3 you should start DFS from 3 as well. Now from 3 I wanted to go to 2, but 2 is already visited. Then I should trace back, like I shouldn't visit it. So there is no way from 3. There is no way from 3 which should be visited, right? Now it's like a trace back. You put it in the stack. So my stack, this is exactly opposite to the DFS, right? So my stack will have this. So once you have completed DFS, then pop out the values in the stack. Here when you pop out, what will come? 3, 0, and then 4, and then 1, and then 2. This is my topological sorting output. This is so simple. You are just doing the DFS, but the only thing is, in DFS, you pop out when you trace back. Here, you should push into the stack when you trace back. That is the only difference. Now you remember, right? When you have to, this is the topological sort order I have obtained. Now let's check. 0, 1. There is an edge, directed edge from 0 to 1. So 0 should come first and 1 should come next. In my order, is it following that? Yeah, 0 came first and 1 came next after 0. Yeah, that this edge is following the topological order. And 1 should come next to the 2. Okay. See here, 1 is present first and 2 is present next to 2. This is also followed. And now 3 should, like if you see here, there is an edge from 3 to 2. Okay, so 2 should be started after 3. Now if you see the condition, ideally you should have like this. If you consider this way, the edge this way, 3 to 2, 3 should come first and 2 should come next. If you see, 3 is here and 2 is here. This is also following the topological order. Now if you see the edge from 0 to 4, 0 should come first and 4 should come next. Okay, 0 came first and 4 came next. And there is an edge from 4 to 1. 4 should come first and 1 should come next. 4 came first and 1 came second. So this order, in this particular order, all directed edges are following the topological order. So if you remember the definition I have written here, topological sorter is a linear ordering of vertices such that for every directed edge, vertex u comes before v in the ordering. So the same happened here. This is an ordering. For every directed edge, vertex u came before v. That's what, right? So on the simple process is you just do a DFS traversal, but the only difference is when you trace back, you push it to the stack. And once your DFS is completed, pop out the values from stack. And there can be multiple topological sort orders that can be possible. In this example, if you see 3 comma 0, instead of 3 comma 0, I would have written 0 comma 3 also. 0 3 4 1 2. Even this is also one of the topological sort order, because for 3 there is only one edge that is going to 2. So I can either put 3 here. I would have put 3, this is one order, right? I would have put 3 somewhere like this, 0 4 1 2. I would have put 3 also here, something like this. So, and even I would have added 3 at the fourth position, like first place, second place we have seen, right? I would have put 3 here as well. So there can be multiple topological orders that can that can exist for a graph. It need not be a single topological order. Okay. Yeah, and coming to the time complexity and the space complexity, to determine the topological order, we are just doing the DFS, right? So the time complexity of DFS, we know it would be the order of V plus E, because we are traversing all vertices and all edges here. So even for topological sorting, the time complexity and space complexity remains same. So order of V plus E is the time complexity, and space complexity would be order of V. Because even if you don't consider this recursion stack, you have to have a set or some array kind of thing to store the values, to store visited value against each vertex, right? For that, the space complexity would be order of V. Yeah, thanks. In the next video, we'll talk about Kahn's algorithm.